I think many of the processes that you have to do, you can do with robots. I think that's the learning curve that's going on right now. The alternative is a huge investment, of course, of a big CNC machine. That's all.
Yeah, you've seen a lot that the CNC machines the moment stay, but all the deburring optimization is all done by robots as a first step.
But this is also apart from the learning curve, as you mentioned, Joakim, that now you have what you have. You have plus minus 0.2 millimeters on an M8 hole somewhere in the corner. You have to design to live with it. Otherwise, you need to do a big fixture for 20 million euros or something. Crazily expensive. I mean that is how to design for manufacturing, I would say.
No, definitely. No, I think that we see, and we also have some deliveries on the theme to some of the OEMs as well. But I think to manage the CapEx and the investment, I think that's a key.
Hello and welcome to the Goldcasting Podcast. The podcast, as you know, where we discuss how to make the most profit and success out of aluminum foundry business. And today we are super excited because today we have Joakim Rosenqvist with us. Now, we happen to know Joakim, you don't, so we will let him introduce himself. But to start with, he is the global sales manager for ABB Robotics, meaning the orange guys working without any vacation in the foundry, day in, day out. So, please, Joakim, could you please introduce yourself a little bit and your history in short?
Yeah, so let me just add a small correction only. I'm one of the sales managers at Robotics, but I'm focusing specifically on automotive and the tier one market, supplying to the great OEMs and so on. So, short introduction. Well, robotics is, of course, super important for the automotive industry, and it's kind of like where everything was started, and really has had a renaissance year after year, and the volumes keep going up. And I think the need for automation is still super high, and it continues to increase. And I think also in the segment that you're working with, in the foundry segment, I think there is much more room for automation, especially when we're talking about megacasting and other things like that.
Exactly, that's the point we want to talk today. But before we dig down how to produce the gigacastings and how's the process flow, I think it would be great if you can give us all of our viewers just a roundup how the production looked like when you have 70 pieces and you have to build a rear floor individually.
Yeah, so the impression, I'm not an expert on foundry, I should say that, but obviously building a car, it contains thousands of parts, and I know that body shop, that's the area where everything most kind of, if you take away paint automation, I think in the body shop that's where the big automation took place first, and I think there are thousands and thousands of robots building car bodies today. So, of course, going to gigacasts or bigger casted parts, it has a significant impact on the way you produce the car, of course. So that's going to be a big transformation. And looking a little bit more on the trends and tendencies, I think that it's clear that we're moving in this direction. I think many of the question marks when it comes to gigacasting is starting to be answered. I think there's a learning curve right now taking place in the industry where those that was early on building big gigacast like Tesla, but many of the Chinese companies and also European companies like Volvo, for instance, they start to realize that there are significant benefits in building a car with the alloys and bigger part. So,
what does it mean for you then? I mean, before you sold bundles of robots for assembling all these parts, are you selling the robots to the foundries now instead?
No, I think robots, in fact, if you see, I mean, if you look at the die casting application today, I mean, it's hard to believe that much of that work was done by humans at some point in time. That's been automated for ages and will of course be a significant part for making a gigacast also. But I think obviously there could be reasons to be a little bit nervous and concerned. Maybe there will be less robots because, I mean, if you reduce car, but several hundred parts, which you do actually when you look at the car body, you might be concerned that there will be less robots. And I think that is fair to some extent, but we also see that the robots get bigger. You need more reach, you need bigger grippers and so on. And I think also it's opened up for new areas, for instance, like in the milling and drilling and deburring and post die cast treatment. I think that's where we will see the biggest impact on it. So bigger robots, I would say, maybe less, but certainly a little bit bigger.
So bigger robots, and you move more, I should have put a secondary process into the line, like drilling and deburring.
Yeah, so one of the concerns I think in the industry is on the investment. Obviously, a big die-cast machine is they're getting much bigger. And when you go up to 8,000-9,000 tons, I think that obviously there's a significant impact on the investment. But I think maybe after the first generation of cars, that will be an investment that you can harvest, and maybe the dice will be the biggest investment going forward. But I think instead of big CNC machines, maybe you can use robots to do a lot of this machining part.
But where do you see the market then? I mean, according to me, most big machines have been sold in China.
Yeah, certainly China is an area where we've also started. Sure, that's where our competence center also happens to be located in this area. But I think most of I'm guessing, and I have to say this is a non-qualified guess, but I think that I believe strongly in this, that there's going to be Gigacast is going to be a part of a modern car. I think all the Western manufacturers also will follow.
But why do you think that we found the development so much slower in Europe? I mean, it started in California around Elon Musk, and then we have seen that 80, 90, maybe even 95% of all the big contracts out of these, we said 110 die-cast machines, 6,000 tons or bigger, are in China.
I don't really know the right answer to that question, but I think maybe there's a little bit more conservatism and different way of calculating return on investment and so on. And I think maybe some of the question marks on whether it is the right strategy when it comes for crash resistance or how to really make the Gigacast. I think that's also taking place now, that there are some people moving forward ahead of the others, and others are looking and trying to understand what's going to happen. But I listened to someone representing Volvo at some point here, where they said that some of the ambassadors are now found among critics once they start to learn how to design a Gigapart. I think they learn that you can't see it as a replacement of a few hundred parts that are joined together. I think you need to see it as something different, and that I think is a learning curve.
Yeah, you have to do a step back and see your overall production, and then see where you can take some shortcuts with the Gigacasting. Because it's not just switching out 130 parts, as you mentioned, for one part. You have to redesign your whole production and also your supply chain.
Yeah, definitely. But it seems that most of the questions, if you look at the from environmental perspective, which is super important for the OEMs, that sustainability equation looks much better when you take away all the transportation, all the handling of these hundreds of parts, and have to focus on one. Maybe it will be the biggest impact on CO2 might be the alloy, and whether you can use recycle or not. Seems also be quite difficult if everybody wants to go for a recycling strategy. There's going to be a shortage on recyclable material. But I think from the environmental perspective, I think it looks positive. I think also the complexity will be a little bit less parts, less complexity, less cost. Seems also that flexibility in design. I mean, you have a form factor that is pretty fixed, that as long as you don't go outside of that form factor, you can have high flexibility in making modification for different design changes and so on. And ultimately, what is most important, I think, is to reduce the cost. So I look at it quite in a positive way. It seems that also the industry is going this way and see it the same way.
Do you see a difference between the guys casting with those big machines? Because we find that most investments are made directly in the car companies. not the traditional die casters all the time. And I see different attitudes. If you work with a traditional die caster, and then you have a couple of meetings with one of the car makers just investing in a bunch of big machines, they're totally completely different.
I have to confess that I have not seen any amongst any of the sub-supplier tiers that is moving for gigacast and making this kind of investment. Even though I came across one just recently in a Turkish company that had actually bought big die-cast machines from one of the OEMs, some reason were being used. So I think it's starting to move outside of the OEMs, but it seems that, and I think that they see this really strategic. So they want to really leverage on the knowledge and the know-how here. But I also think that follows the pattern that where you have to have the die cast machine close to the body shop.
Absolutely.
Right?
But a lot of China and Europe we have discussed. What do you think about the North American market?
I mean, Tesla, they started in California. I believe the first investment was in California. If you correct me if I'm, better.
Yeah,
than
it was in Fremont.
Yeah. So I think we see that the import duty, I mean, the tariffs that are being increased is now 100% on electrical vehicles. So I think definitely there has to be investment in North America. The question, I think, maybe if the North American market is ready or not. When you drive there, you see a lot of Teslas, of course, but it seems that it's moving more to hybrid vehicles currently. But I think the trend is quite clear. It's going to be a lot of fully battery cars also in North America, but maybe they're a little bit.
But sometimes I wonder if that is a problem, because I think there's a strong carryover. Using a gigacasting that has nothing to do with the drivetrain. You can build a diesel car with a casted rear floor if you like.
Right.
So if you go this direction, that is proportion variance doesn't affect the choice of the chassis build or body wide build. Of course, yeah, you don't have a battery, but otherwise they look pretty the same with the shock towers and the rear floors and the side beams and what have you. So for us working with big structured castings, I think we are pretty happy regardless what they actually build and sell. I'm more worried about the sales volumes, especially for Europeans. But I get a feeling the sales volumes in North America is going up, but not on electrical vehicles.
No, it's a quite small part. I think even though it's 10% of the total sales is battery. I don't know how much that is in Tesla, but there is also a kind of like a dilutive effect that there are so many. I listened to a seminar on the matter in the US where there was a person saying that when you sum up all the big SUV manufacturers and that wants to go electrical, there's many of them, and they get quite small volumes for each. And then, of course, I mean, if you want to carry an investment of a 8,500 or 400 tons die-cast machine on a small volume, it gets difficult. So that could be one of the reasons. But
if you go for an EV, there are actually 3 castings you can do on that machine. You have the rear floor, you have the front of the car, and you also have the battery box. That you can do on these machines, and then it's probably fully utilized and even overutilized when you go in that way.
As I said, I don't really have the answer. I mean, it's a question to follow and really track, but I think that there will follow. I think also if you look at the ones starting with the gigacastings, a lot of them are new entrants and new contracts and new models. Tesla, you have Li Auto in China, you have BYD, you have many of them are not traditional car companies, I would say. Volkswagen, Volvo, etc.
Yeah, one of these non-traditional car manufacturers like Xiaomi, it took them 3 years to go from publishing a concept into selling the first cars. Is that also something that gets better with the gigacasting and also implementing more automation that you can level up way faster production? You don't have to wait 7-8 years to build up the platform.
I think what we have to remember, even though we are in the business-to-business industry, we are heavily dependent on consumers and what they like and don't like. I think it's not so easy for an OEM to take these big decisions not knowing whether a platform will be successful or not, or a car model rather. I think they need to have a platform mentality that gives them options depending on how it works. But I strongly believe in this. I think that makes perfect sense once you start to clear out all the question marks. I mean, from strength, durability, and cost, weight. I know stiffness was one of the discussions also early, that whether this kind of aluminium alloy would have the stiffness needed to resist a car crash. But it seems that once they start to learn how to design and build the strength, they realize that there are benefits here also. And I don't think anybody envisions that after a crash that you will be able to recover the vehicle and repair it. But
Probably not.
no, but I think also if you get a severe crash on that level with the conventional car part, you need to scrap it anyway.
Yeah. It goes twisted and bent and all that. But
yeah, even if you're a normal car, you have so many glue areas, rivets, and you cannot replace them. You have to replace anything or scrap it as a whole because it's too expensive to replace. Therefore, there's not too much of a difference.
But for mild touch, it seems that they can have the resistance and the strength that is needed also.
Yeah, with the Gigacasting, you can implement so many different load paths without going from one part to the next one, which always is a loss in stiffness.
So from automation point of view, I think the machining has been raised as one of the drawback, that you need to have expensive machines to mill and drill and so on. But maybe with robots you can have the flexibility that you can do this to a lesser investment cost. But I think that's where you see the big automation, at least coming for Gigapart.
But we in this pod, we normally claim that it's probably 10-15 years of our journey and development from now onwards for alloys, how to design, how to make it lighter, post-processing, everything. Would you agree or would you disagree on this statement?
No, I can't agree or disagree, but the impression I have, at least from following it on the side view, I think that we're learning pretty quickly and learning fast, because these projects is not on the research level. They are taking place. I mean, they're building cars with gigaparts today, and obviously you have to, if you're going to put it on the market, you need to be to a high level of certainty, know what you're doing at least. And maybe that's in your being expert on die casting. Maybe that is more a question in the business, in the industry. If it's enough, or if it's moving faster, then it's good. But it seems to be great awareness anyway.
Yeah, it is. But I think the big thing that people are trying to figure out is actually this with quality and quality defects and properties. Because I mean, it's sad to say, but the sheet metal guys, they have the perfect material. It is clean. It has the same elongation, the same properties in all direction and all that. It never surprises you with a big defect. In casting, we take a perfect material God given, and then we do our utmost to ruin the properties by making oxides and inclusions and porosities and stuff. And I think here lies the big development, that how do you actually cast 40, 50, 60 liters of aluminum in a way so A, your machine is running 80-90% of the time, and B, you have a very well-defined set of properties all over the whole casting. That's why I'm saying 15 years of development, because I think I'm just handling that volume is difficult without getting a pre-solidification somewhere or something dripping down, or it's messy if you compare it with sheet metal.
Yeah, but complexity seems also be a little bit lower. I mean, you don't have 400 parts that I heard. I mean, a gigacast could replace in a car body. I mean, you have less complexity at the same time, but it's a different technology and a different process to master.
Mm-hmm.
So maybe the early learnings now on the first generation of cars will quickly be implemented on the coming generations.
Yeah. And we are happy, because the Gigacasting, they have meant that finally, after years and years and years of decline since the 90s, our industry is seeing investments, money, and if you're an educated guy or girl and some good curiosity and some couple of years of experience, tell me where you want to work. They're screaming of the people around the gigacasting investments. They need people in tools, alloys, process, machines, whatever. Because people are, for once now, not expensive anymore if you compare to the investment.
Also, if to the cost if something goes wrong, as the whole car production is standing behind it. And there are a lot of people working, and that's the cheap thing. If it comes down, everything goes through and you're having a recall later on. That's the thing you have to avoid. And especially, how do you check these parts? As they're running out every 90 seconds, another part, which are way too big, way too heavy to handle by hand. Is that something that you see a lot of requests for your robots to handle the parts for quality checks and throughout the production?
Yeah, I can't give any example of it, but certainly after you take it out of the die cast, I mean, there's lots of things that needs to be taken. I mean, you don't want to spend a lot of machine hours on a part without knowing that it's going to be used downstream, so to speak. I think that I know that there's been a lot of talk in the industry about scrap rates, but I think they started high, and it seems that it's going down. But I think this is the whole knowledge building that's taking place now. I'm pretty sure that I think what is not going to be changed is that the level of scrap rate that you can afford. I mean, that has to be super, super low. So learning how to master that, I assume the industry will manage.
But you're selling robots.
Yeah.
If you speculate about the areas of interest coming years, what would you see besides robots? And the borderline of automation.
No, I mean what is clear if you look at the OEM. In the beginning of the electrification, we talked about high mix and the increased need of flexibility and scalability. I think more than ever, at least right now, because you see there's some moving back from purely battery to hybrid vehicles. You look at the commercial vehicles, you will see a mix of, they're even developing new combustion engine platforms to run on CO2 neutral fuels and even hydrogen. So you see even a greater need for flexibility and scalability, not the least. So I think we will see a mix, for instance, use of mobile robots to really redesign the way we build lines. The body and white lines where there is a constant flow. I think we're moving away from that, and you will see islands of cells that you transport parts to rather than in a line concept. And then you can increase also the flexibility because consumers' demand for variation and the customization will be even greater. So how do you manage that?
Is that why you see Tesla doing this in Fremont now? They're tearing down the line.
I don't know exactly what they're doing, but I see it in many other. If you look at from a tier one perspective, where you're taking a contract for an OEM, of course you want to see that the volume that they're promising will real material. So maybe you don't want to have a big CapEx investment for the full volume coming down 3, 4, 5 years from now. Maybe you want to have a scalable solution that can start with 40,000 or 80, 120, and so forth. That we definitely see examples on, and we also see then examples where the design solution, in order to have this flexibility, you use mobile robots and then you can, with a clear understanding where you have your bottleneck, you can make the investment there instead of read the whole line on multiple things.
But when you say mobile robots, are they standing on small wheels and traveling around, or is it just that you?
Commonly known as AGVs, it's AMRs where you move the parts with on top of the robot, the mobile robot. I mean, it's an automated guided vehicle basically. So instead of having failures and this kind of transportation solutions, you can move the parts instead.
Yeah.
Interesting. Is that also a solution to build cheaper cars, because if you look at the EVs now, they are way too expensive for the mass consumer market.
I think, we're all consumers. We know what it costs the fully battery cars, but I'm uncertain. Just by looking at the simplicity, and I think obviously Tesla is driving this, they're in the forward, thinking in new ways. How do you assemble a car in the shortest way, the shortest lead time? It's a way, we're stepping away from the Ford concept with the move line and going to more distributed cell-based solutions. So I expect cost to be a continuous pressure in the market, and it's driven by the consumers, of course. We don't want to pay what it costs today.
Speaking about the consumer, we from our end, we hear quite some projects now being halted. Also see that other platforms are being pushed forward instead of waiting, especially hybrids. And in Europe, we have a quite dreadful situation among the foundries. They have had filled order books, but energy prices have eaten up all the margins. So now when we seems to have a downturn in number of cars, you're standing there without any cash. Do you feel the same at ABB, that it is a little bit harsher out there right now?
No, I think from the robot industry is always impacted hard by when the car industry or the automotive industry get the flu. Robot industry take a hit. We saw that coming from Lehman Brothers period. We came from the COVID and the semiconductor. It impacts robot industry. Robots is significant has a significant importance to the automotive industry. So I think right now, hopefully it's only a short-term hesitations now on where to go from here now. I think it's anyway clear that there's going to be a lot of investment in the automotive industry moving forward as well. But it seems to be an uncertainty. Well, is it fully battery? Is it hybrid? How do you manage the complexity in it?
A market with a higher level of flexibility in most dimensions. We're speaking about electrical, hybrid, or diesel. We speak about different models. Even you have systems for robots moving around where they need it most. And no one is really sure on out of all the newcomers who will actually survive on the market. So it's a little bit like playing volleyball with a jellyfish.
No, what is clear anyway, that you can't build cars without robots. That is clear. And I don't think Gigacasting will change that. It's just that the applications will change. But it is a significant change, of course, to the automotive industry, the way they've been operating for decades. But it seems anyway that the acceptance of Gigacasting is quite high and more positive feedback. And from ABB's point of view, I think we see definitely milling and machining and drilling in this kind of post treatment of the parts is one area. Material handling, maybe quality inspection as well. And then, of course, the way you design automation using mobile robots as a more natural ingredients in the automation.
I have to dig a bit deeper into the milling operation. As far as I learned in milling, stiffness and not moving the parts while machining is the most important thing, that all the cuts are in relation to each other. And with the robots, there's usually a bit of flex. How would you do it with the robots? Is there a different clamping system, or does the robot put it in a fixture?
No, I think that robots are getting much bigger and stiffer for many reasons. But obviously, you need to fulfill the quality requirements and dimensions and how much. Because you're right, an extended robot arm has a certain flexibility. But I think many of the processes that you have to do, you can do with robots. I think that's the learning curve that's going on right now. The alternative is a huge investment, of course, of a big CNC machine. That's also.
Yeah, you've seen a lot that the CNC machines the moment stay, but all the deburring optimization is all done by robots as a first step.
But this also apart from the learning curve, as you mentioned, Joakim, that now you have what you have. You have plus minus 0.2 millimeters on an M8 hole somewhere in the corner. You have to design to live with it. Otherwise, need to do a big fixture for 20 million euros or something. Crazily expensive. I mean that is how to design for manufacturing, I would say.
No, definitely. No, I think that we see, and we also have some deliveries on the theme to some of the OEMs as well. But I think to manage the CapEx and the investment, I think that's a key. But I think once you've done that on the first generations, I think you can you don't need to redo it moving forward. But what? Because I think the fixture and the joining points of a gigacast, that is where you have the highest vulnerability. I think that you need the strength and so on. And obviously, I mean, if you're going to assemble it, you have to have the right tolerances now.
Yeah, and the less porosity.
Yeah, but here I think this is your field of expertise. I think that this is one of the challenge because you get big parts and you have to design the die in a certain way to manage that, and maybe reshaping what other technologies or techniques is available to manage to get rid of those risks, because I think that is where they have the biggest problem is where is the porosity and the joining points.
And then you think reshaping could be a solution.
Yeah, I think listening to you, I think you are fully convinced that it is, right?
Yeah, but you know, I placed everything. You know, the children's college savings are in real casting right now. So if it doesn't fly, I will be playing the violin outside the ICA here in Täby.
But Staffan got a sign: 10 minutes break is then 10 euros.
But isn't it? I mean, in your industry, the die cast guys are the most popular and hottest guys right now out there in the industry, in the R&D departments, maybe moving away from steel. Yeah.
Oh, I think my biggest struggle in my daily work is the learning curve that you're talking about. I mean, if you take a sheet metal-driven engineer or chassis components, he's spoiled with the tolerances you get in sheet metal production, because that hole that you punch is plus minus 0.005 or something. It's about the heat elongation of the sheet, you know, depending if it's 18 or 27 degrees in the workshop that day. So, and then you come to die casting, which is, again, a beautiful way of ruining God's best material by introducing all the defects we can in a possible manner. So when these two worlds meet, that's my biggest challenge in my daily work.
Yeah, especially I don't think that the people knowing how the things work are the problem. It's more like that you have specifications designed for a totally different process, and now you try to apply them because you cannot get rid of them, and you're standing in your way for yourself with the specifications you have in place.
I think the elephant in the room I tried when we're talking so much about China and Western Europe and North America. What I'm trying to get is, I think in China the culture is that good enough is good enough. The perfect is not standing in the way of the good, and it's more important in China to produce the first 20,000 cars with a gigacasting. And then maybe they realize that elongation is only 5.5% in this right corner, but hey, let's produce some cars instead, and then we learn. And in Europe, we try to get the elongation to 7.5 or 8.5 or 10.0. There's different values here. And then we're disappointed, and we're firing people, and we add another year, and we delay our chassis start of the production of a new chassis. That is the feeling I have.
But don't you also think that if you produce thousands of these parts, you gain a great amount of knowledge?
Yes and no. Yes and no. Yeah, because again, I agree, because you have quite new organizations with very limited experienced people. Because how can anyone be experienced in running a 6,000 ton machine? There are not that many out there, and the only one that has real production data is actually Elon Musk, Tesla, or Hydra, the supplier of big machines.
Yeah.
So in that sense, I think you're right. But what people tend to forget is a data sheet of properties is something that is very often produced under perfect circumstances in a very small scale, 20 centimeters. And now we're looking at 200 centimeters instead. And then you have physical factors that starts to influence. And I think it's actually impossible to reach some things. I mean, otherwise we will take an Airbus to the moon if physics weren't around, right?
Yeah, definitely. Also, you see that maybe you need a different setting for these parts, especially they're so big, and it doesn't count that one small area has a different elongation, because the load path can go a different route and you still be safe. And maybe you have to change it like you do it for small parts where you cannot have any tensile bars on it. You do a part test in a direction which is the load coming from. Maybe you have to go in this direction also for the gigacasting, that you take out one per shift, or the beginning more, than later view less, that you know how is the part behaving in a real-time situation. Because the tensile test is just one directional, and there is no one directional crash. It's always go different ways.
And a tensile test, guys, you have to ruin your part. I mean, it's like testing matches in Norway. You write them and then you say they're okay. It doesn't work in a car production. And my dream and my vision, at least, is this merger of disciplines, that we have to come together much more between different disciplines like tool making and die casting machines and automation guys. You're super important, because the way you take it out of the die casting machine and the way it cools down the first 2 minutes actually makes plus minus 2-3 millimeters of gigacast. So I mean, these things are important, but I think this is the time when we will see machine learning being used in commercial products very soon. I mean, even Comtech, 28 people in the wood, is actually doing research on AI and machine learning. Because how should you otherwise get all these parameters into one page?
Yeah, maybe the time of the age of industrialization with AI is the big. I mean, what significantly will change it, because it's what you say. I mean, it's everything from the alloy, the die, and the process parameters, process equipment. At the end of the day, also the design of the part that will decide whether you get the output that you need, so to speak.
It's so many factors involved in such a big casting that even the smallest change counts, and then you have to find a way. How can you counteract on that? For example, if you drop in the silicon content, then you have to increase the temperature of the shot sleeve or whatever. Just making up figures here now.
Yeah.
But that's something you never get if you're just a human standing there checking up on the data sheets in 1 second before the shot.
And here lies, sorry for being philosophical here, but here lies the big difference between sheet metal chassis and casted chassis. Because in casting, you have trends. The tool gets more and more worn. There are a lot of things that happen. It affects much more. In the sheet metal production, if the tool is worn, you see it directly. If the welding doesn't go way as planned, you see it directly. But here we pour a big bucket of aluminum, we shoot it in a speed of 150 kilometers an hour into a tool, 50 million Swedish kronas, and you don't see anything, because it's just a cube of steel, and out comes something. And you cannot test it. Because here comes the problem again. If I want to test it really on the zone that it matters, I have to break the part and make a tensile test bar. But in the sheet metal, meter 1 to meter 50 on the coil has exactly the same. It's like a blended whiskey, famous Browse. Tastes like it should every year. And here we comes with a single malt, So when you buy your Tesla, the guy says, well, Staffan had a little bit of a bad day, so don't crash, this car, because that will not, please don't. So this is why I'm saying, sorry for making a joke here, but AI, artificial learning, merger discipline, 15 years of development, and a fantastic development. I'm looking forward to be a part of it.
But don't you think that the alloy development will be the answer to many of these questions?
No.
You think it's still be the traditional what we do? Because I mean, the requirements on the alloy is also changing, and
yeah, it will be part of it, but not. It's not a solution, because you have a big pile of problems here. Number one, everybody wants recycled. Look at the aluminum you have out there in the market. It's actually crappy twitch, containing copper, iron, a lot of things that makes the elongation go low. So that's the first problem we have. The second problem we have is that if the alloy development is the slowest thing on this globe, believe me, if you want to invent a new alloy that is accepted and put in production, take a pick. Ford, Volkswagen, Daimler, whatever. You're looking at a 12 to 15 year journey from today until you see it in a car.
Yeah,
Definitely.
it takes 7 years until you can do the first trials at the automaker.
Yeah.
And then you have to wait for the next platform if the tests are gone. So there you
go. I was actually at a meeting in Europe, and there's a group of car companies involved, and one of the smaller car companies in this group, ownership group, had an idea of using a 42,000 alloy. And then I said, why don't they blah, blah, blah? And then my customer said, please don't speak about this, because that is the worst political discussion you can find right now. People are shouting and swearing, and you really, it's like the parliament agrees. So, I mean, alloys, yes, you're right in the sense that, you have to use lower silicon, you have to do a lot of things. At the same time, you have to keep an eye on the sustainability of the thing. So my guessing is that, yes, there will be some alloy development, but it will be the learning curve that you spoke about in the beginning, Joakim, that the designers have to design for more crappy material with lesser properties that still shock absorbs, because otherwise no one can build an electrical vehicle on secondary alloy without paying like crazy. Then you can, but who wants to pay like crazy?
It comes down to the structure. You have two ways how you can absorb energy. It's from the material, and the other one is from the structure. And if you have a big structure, then the structure has to do it and do the heavy lifting for the material.
But I think we're forgetting this, how you actually test them. How do you guarantee that you have the desired properties in place when they ship in this big rear floor into your production line? That is the big thing, because I mean, the only thing you need, the small thing you need, is 25 degrees cooler on one spot of the tool when the shot goes. And how do you guarantee this? And in real time? A lot of people will be very wealthy if they have solutions on these things.
I certainly don't have the answer to that question. That I can from ABB coming from the automation side. But I'm thinking also about this. It seems that the OEMs are quite keen on getting back what they sell. Also, I mean, also in this regard, because not only for the from cost side, but from sustainability point, to be able to recycle and reuse to get to it. And it's the same for batteries, to be honest. So I think we will see more of a circular economy.
Yes.
Used cars or scrap cars is going to have a certain value, and you want to reuse it. But obviously, if the alloy has a super important part of the end result, obviously you need to control that.
Yeah.
Especially you need to control the extraction process, because if you just put your car through the shredder and sort out what comes down there, you will never get a good alloy. You can just sort aluminium and steel, and that's it. And you have a bunch of things no one wants. And going for large castings, which are easy to dismantle, and then you have one big pile of one alloy, that's something you can easily recycle.
I mean, this is also a common challenge when it comes to battery. How do you disassemble a car in a good way? Having to do it fully manual, and that's like you point out, Fabian, that you don't want to mill. I mean, to just put everything into a super mill, and then you get. Maybe it's easier on the battery side, where you want after chemicals, where you can enrich and get that out of the chemicals. But robots could play a role here as well on the afterlife, so to speak.
You'll see more and more automation and more robots, believe me, around the Gigacasting machines. When people start to realize the saving in handle with care, handle in a certain way, and doing small artificial aging bumps or whatever in the process. Coming 10, 15 years will be super interesting.
Yeah, I mean, from a robotics perspective, I mean, we've already automated. I think that will not change the die cast process, but also when you take it out of the die, that's done by a robot, and then obviously it's better to keep the orientation of that part and do most quality spectrum, taking away the parts that you don't need, and then also to modify it, to machine it, so to speak, with robots, and then straight down to assembly lines. So that, of course, is the ultimate way, I think.
Absolutely. And as you said, you know where you have your part when you grip it in the tool. It can never be more precise.
But I think we will see, it will take some time until we see that unbroken change to materialize. I think right now the industry is trying to master the die cast process and make sure that they get out of that process on the cycle times that they need and so on. And then they will start to think about the next steps.
I think you're absolutely right. And I think that is a perfect ending of this podcast. So thank you very much for being with us, Joakim. And as always, a pleasure talking to you.
No, thanks for having me. As I said, not the expert, but bringing it from a robotic perspective at least.
Very interesting perspective.
It's really interesting and was talking to you and seeing how it changes, because we thought at the beginning, if you go for the high pressure die casting and a gigacasting, you will have less robots, but it's great to have that refreshing view. And if you want to have more refreshing views, don't forget to subscribe, and we see us in the next Gold Nugget. Thank you.
Thank you.
Goodbye.
Bye-bye.
Thank you.